So in today's video, we're going to talk about how to make an acyl chloride from a carboxylic acid. Now, carboxylic acids are widely available in nature and therefore cheap, and we can get a wide variety from nature, differing the R group here. So if we can make our acyl chlorides from carboxylic acids and therefore make carbenes, we can get a wide variety of carbenes in a cheap manner through these simple reactions. So we're going to be looking at the mechanism to generate these acyl chlorides. We're going to use a carboxylic acid, just a generic with an R group. We can vary this to be pretty much anything. Reacting with thionyl chloride, and we'll see the structure of that, and like I say, we'll see the mechanism shortly. Going to our acyl chloride here on the right. So this mechanism is a little different to what we're used to seeing, as we don't attack our electrophilic center on our carbonyl here. We actually use the carbonyl here as a nucleophile. I should mention this is our structure of the thionyl chloride. What happens is a pair of electrons moves in, forming a double bond between this oxygen and the carbon. The double bond is our nucleophile and attacks the electropositive sulfur center here. This makes chlorine leave as a leaving group. We then get a structure where we have an oxygen sulfur bond form with an oxygen there, an oxygen there, and this is protonated. So now the chloride that is left in our first step comes back in and attacks this electrophilic center of our carbonyl. So our chloride is now acting as the nucleophile. When it does so, this moves the electrons back onto the oxygen, getting rid of that positive charge. This creates another intermediate now where we have our chloride bound. We have two oxygens with a single bond. We still have that bond to the sulfur. And now we get our lone pair on this oxygen come back in again, and this carbon can only have 4 bonds at one time. So it kicks off this oxygen as a leaving group. So we then got an intermediate now where we have our R group, our chloride, we've got a double bond oxygen with a proton. So we've got a positive charge, we've got 3 bonds there. Our OSOCl, this oxygen will be negatively charged as it left as a leaving group, taking those electrons with it. This can deprotonate our acyl chloride that we now have here. This gives the electrons back to that oxygen, and we then form our acyl chloride. Like I say, we can vary our R group here, and doing so will give us a wide variety of different acyl chlorides. All we have to do then is react these acyl chlorides with diazomethane, which we will see an example of in the next clip. So here we've got our acyl chloride and our diazomethane, and I've already drawn it in the resonance structure that we need with a negative charge on the carbon. Now the carbon comes in, acting as our nucleophile, attacks our electrophilic center there. The pair of electrons in the double bond here moves back up onto the oxygen, moves back down and kicks off the chlorine as a leaving group. And when it does so, we get our intermediate before the diazo compound form now, where we have 2 hydrogens on this carbon. We have our 2 nitrogens there, and now we can either have another molecule of diazomethane or a base come in, basically something that can take one of these protons. It'll take one of the protons, the electrons will be given to the carbon, and we will form our diazo compound now, where we have a negative charge on our carbon. We have our nitrogen leaving group. All we need to do is supply some heat or some UV light to get rid of that nitrogen as the leaving group. And we're left with the lone pair on the carbon, and we're left with our carbene. So in that previous segment, I talked about how we can use diazomethane as a base instead of adding another base in. If you use two equivalents of diazomethane, you can react with your acyl chloride and then use the other molecule diazomethane to take a proton to generate your diazo compound. So you get rid of a proton from your intermediate. Now, the reason we need an acyl chloride to do that instead of a carboxylic acid is because obviously, as the name suggests, this carboxylic acid is an acid with a pKa of around 4. So this diazomethane, acting as a base, can take a proton from the carboxylic acid and therefore not act as a nucleophile to our electrophilic center here. So we won't get leaving of an OH or anything like that. We'll get deprotonation here, electrons being given to that oxygen. We'll form our carboxylate anion, and then we'll have a molecule of diazomethane now, where we have our carbon with 3 hydrogens bound. Now, as we know, this N2 is a really good leaving group. So what will actually happen is our carboxylate will act as a nucleophile attacking our carbon here, and our nitrogen will leave, and this will generate an ester. So this is great if we wanted an ester, but obviously we were going for something that we could make N2 leave and generate a carbene. So now we've got this ester. This is our product. It's not what we were going for. Esters are widely found in nature as well. So this may not be a very efficient way to get to an ester when you can extract it from nature. But using this carboxylic acid to generate your acyl chloride is a really good way to get lots of different acyl chlorides really cheaply, and therefore get a lot of different carbenes really cheaply. So in the next video, we'll talk through the reactivity of these carbenes, looking at C-double-bond-C insertions, CH insertions, reactions with NH and OH, and also the Wolff rearrangement.